Welcome back. In our previous session, we defined odds as a simple comparison, the frequency of an event happening versus it not happening. To illustrate, imagine blue circles represent a student passing and red circles represent a student failing. The odds are calculated by dividing the number of students passing by the number of students failing, such as 2 divided by 4, which is 0.5. However, here's where things get slightly confusing. People often use the term odds ratio. What does that actually mean? It is quite literal. An odds ratio is simply taking one set of odds and dividing it by another set of odds. For example, comparing the odds of two different groups passing the exam. However, this introduces the exact same visual and mathematical bias we saw before. If the bottom number, the denominator, is bigger, the entire result gets squished into a tiny fraction between 0 and 1. If we reverse the numerator and denominator, and the top number is bigger, the result can rocket upward infinitely. The scale is totally lopsided. The fix remains the same. We apply the natural logarithm. By taking the log of this ratio, we stretch out that squished space and pull back the infinite space. Suddenly, a ratio tilting one way gives us negative 1.79, and tilting the exact opposite way gives us positive 1.79. Perfect balance is restored. So why do we actually care about this? Let's look at a real data set. Imagine we are tracking 400 learners. 40 passed their final certification, while 360 did not. Now let's introduce a variable. We tracked who completed the hands-on linear regression project before the exam, creating a data matrix. 150 students did the work, and 250 skipped it. We want to measure if doing the project actually improves the chances of passing. First, we calculate the odds for the students who put in the effort. For those who finished the project, 30 passed and 120 failed. Their odds of passing are 30 over 120, or 0.25. This becomes the top half, or the numerator, of our master equation. Next, we look at the group that skipped the practice. Only 10 passed, while 240 failed. Their odds are 10 over 240, or 0.04. We slot this into the bottom half, the denominator, of our equation. When we divide the top fraction by the bottom fraction, we get a clean result, 6. In plain English, this means a student is 6 times more likely to pass if they took the time to complete the practice project. To make this result mathematically useful for modeling, we take the natural log of 6, which is 1.79. This log odds ratio is an effect size metric. Just like R² tells you how well a line fits data, it tells you how strongly these two variables are connected. But an effect size isn't enough. We have to prove it wasn't just a lucky break. We need statistical significance. Data scientists generally use one of 3 tests for this: Fisher's, chi-square, or the Wald test. Since the Wald test is a powerhouse, let's focus there. Think of the Wald test as a what-if scenario. What if our practice project was actually completely useless? If we simulated thousands of hypothetical classes where the project had 0 impact, the random results would pile up to form this exact bell curve shape. Most of the time, the result is exactly 0, meaning no difference at all. To map our specific data onto this curve, we need its standard error. We calculate this directly from our raw numbers. The result, by adding the inverse of all 4 groups and taking the square root, is 0.38. Now we just see how far our project's score lands from the center of that random curve. By dividing our log odds ratio of 1.79 by our standard error of 0.38, we find that our result is 4.7 standard deviations away from the mean. In statistics, landing more than 2 standard deviations away is generally considered significant. Landing 4.7 deviations away means the probability of this happening by random chance is less than 0.00001. The evidence is overwhelming. The project works. To wrap it all up, an odds ratio compares 2 sets of odds. The log version measures the strength of that connection symmetrically, and the Wald test confirms if it actually matters. You now have the mathematical foundation for logistic regression. Until next time, keep analyzing scientifically. Why do algorithms like logistic regression use the log odds ratio instead of the raw odds ratio? The answer is that raw odds ratios are heavily biased. A negative effect is trapped between 0 and 1, while a positive effect stretches infinitely upward. This asymmetry makes it impossible for linear models to weigh opposing features equally. By taking the natural log, we center the neutral point at 0, perfectly balancing the scale, which is required for algorithms like logistic regression to work correctly. Thank you for watching this video. Remember, every small step is a giant leap toward mastery. Keep upgrading your skills scientifically with Skill Science Academy. See you at the next level.